Hey everybody. Today we're talking about the gamma distribution, which is used to model the time elapsed before a fixed number of occurrences of a random event, like calls to a helpline or defects in a production line. We say that events like that occur according to a Poisson process. I have an earlier vid in my course on mathematical probability on the Poisson process. I'll throw a link to that up top if you're looking for a refresher on that. Suppose the events occur at an average rate of lambda per unit interval, and we're interested in the time before alpha occurrences. The probability of fewer than alpha occurrences occurring in an interval of width alpha is computed using the Poisson distribution. And I've written the probability of fewer than alpha occurrences here. It's the probability of 0 occurrence plus the probability of 1, 2, 3, all the way up to alpha minus 1. And then inside that summation, you are seeing a probability mass function for a Poisson distribution with parameter lambda over an interval of width x. This event is complementary to the event that the waiting time for the alpha occurrence is less than x. And so this gives us a description of the CDF, the cumulative distribution function, of a random variable with a gamma distribution. Usually the gamma distribution is described using theta, the average time between occurrences, rather than lambda, the average number of occurrences per unit interval. Those two are reciprocals of one another. Theta is 1 over lambda, and lambda is 1 over theta. So the CDF of a random variable with a gamma distribution with parameters alpha and theta is given by 1 minus the sum from k equals 0 to alpha minus 1, x to the k, e to the negative x over theta divided by theta to the k, k factorial. Quite a mouthful. This is defined when x is greater than 0. You can't have negative waiting times. We obtain the probability density function, the PDF, by differentiating the CDF and then simplifying. And the PDF actually has a much simpler form than the CDF because the summation can be made to go away with a little bit of clever algebra. This PDF is usually written using the gamma function, which is just a generalization of the factorial to non-integer values. And that allows our gamma distribution to cover values of alpha that aren't just positive integers. When alpha is an integer, gamma of alpha is alpha minus 1 factorial. And so the PDF of the gamma distribution has this form. All I've done here is to replace alpha minus 1 factorial with gamma of alpha. When alpha isn't an integer, gamma of alpha is defined with an improper integral. I'm not going to go into that in this vid. One thing you have to be careful with when dealing with the gamma distribution is that the parameters theta and lambda are both in widespread use, even though they both carry the same information. They're just reciprocals of one another. It's most common to write gamma of alpha comma theta for a variable with a gamma distribution, but you may also encounter gamma of alpha comma lambda. So you have to watch out when you're interpreting problems, evaluating probabilities with technology, when you're communicating results, to make sure that it's clear which parameter you're using, theta or lambda. Let's do an example. On a Saturday morning, customers arrive at a bakery according to a Poisson process at an average rate of 15 per hour. What's the probability that it takes less than 10 minutes for the first 3 customers to arrive? What's the probability that it takes between 14 and 17 minutes for the first 4 customers to arrive? The waiting time for 3 events that occur at an average rate of 15 per 60 minutes has a gamma distribution with parameters alpha equals 3, the number of occurrences we're waiting on, and theta equals 60 divided by 15, or 4, the average rate at which those occurrences happen. Plugging in, we get the CDF that I've written here. We can evaluate this at x equals 10, and we get 0.456. So the probability that the third occurrence comes in the first 10 minutes is about 45.6%. Now, it's not a lot of fun to evaluate probabilities in this way by plugging into this summation formula. So we almost always do probability calculations in the gamma distribution using technology. I use R, where the CDF is represented by the function p gamma. And you need to feed it the value of interest, the parameter alpha, and then the parameter lambda. So for instance, in this last example where we were talking about a gamma distribution with parameters alpha equals 3 and theta equals 4, we compute the probability that x is less than or equal to 10 by writing p gamma 10, 3, 1/4, and that gives us 0.456. R uses lambda rather than theta in its probability functions, so just make sure that you're plugging in the right value there. That's why I have 1/4 in my p gamma rather than 4. Back to that example, the probability that it takes between 14 and 17 minutes for the first 4 occurrences, still with theta equals 4, is big F of 17 minus big F of 14, where big F, of course, here is the CDF of that gamma distribution. So p gamma of 17, 4, 1/4 minus p gamma of 14, 4, 1/4. When we execute those commands, we get about 15%. The values alpha and theta are known as the shape and scale parameters, respectively. Lambda is known as the rate parameter. So you will see that vocabulary occasionally when you are reading about the gamma distribution. The moment generating function of a random variable with the gamma distribution is m of t equals 1 over 1 minus theta t all to the alpha. This can be computed directly from the definitions, although it does take a fair amount of work. I'm not going to go into it right now. Once you've got the moment generating function, you can find m prime of 0 to get the expected value, which turns out to be alpha times theta. You can do m double prime of 0 to get the expected value of x squared, and then you use the formula that the variance of a random variable is the expected value of x squared minus the expected value of x quantity squared to get that the variance of a random variable with a gamma distribution is alpha times theta squared. By the way, I think the formula for the expected value here, alpha times theta, is actually pretty intuitive. Alpha is the number of occurrences we're waiting on. Theta is the average waiting time per occurrence. So it makes sense that if we're waiting on alpha occurrences, we would have to wait alpha times theta units of time. The gamma distribution is always skewed right, regardless of the values of the parameters. If you increase alpha or theta, you are going to increase both the expected value and variance. In this picture, I've drawn gamma of 3, 0.05 and gamma of 3, 1 just for illustration. And these are pretty typical gamma distributions. One more example. At a luxury hotel, towels are stolen at an average rate of 20 per week. If the hotel has a reserve of 100 towels, how long can they expect their supply to last? What's the probability that they'll run out in the next 4 weeks? What's the probability that their supplies last between 4 and 8 weeks? So I recommend pausing the video here, trying these on your own before seeing my solutions. The time elapsed before the 100th occurrence is going to have a gamma distribution with parameters theta equals 1/20th, lambda equals 20 being the average rate at which the towels vanish, and alpha equals 100 because we're waiting on 100 occurrences. So the expected value, alpha times theta, is 5. That's the expected waiting time before 100 towels disappear from this hotel. The probability that 100 towels vanish in less than 4 weeks is big F of 4. We're evaluating the CDF of this gamma distribution at 4. Using technology, that's p gamma of 4, 100, 20. So that's the reciprocal of theta, which of course here is 1/20th. When we do out that command, we get about 0.017. So the hotel probably doesn't need to reorder towels this month. There's only about a 1.7% chance that they run out before the end of the month. Similarly, the probability that x is between 4 and 8 is given by p gamma of 8, 100, 20 minus p gamma of 4, 100, 20. We're doing the probability that the waiting time is less than 8 minus the probability that the waiting time is less than 4. When we evaluate those commands, we get about 98.3%, so the hotel probably will run out of towels during the second month. The gamma distribution has 2 very important special cases that I want to mention as we wrap up this vid. First of all, when alpha equals 1, we get the exponential distribution. So we're just modeling the waiting time for a single occurrence, which is to say the waiting time between any 2 occurrences, when you, again, have a Poisson process. When theta is 2 and alpha is r over 2, where r is just some positive integer, we have the chi-squared distribution with r degrees of freedom. And that models, among other things, the distribution of the sum of squares of r random variables, each of which has a standard normal distribution.